Okay, so again, the just classical Galilean transformation velocity addition rule is just wrong in general, although it's a good approximation. It's a very good approximation at when the relative velocity between two um, coordinate systems, two reference frames, is small compared to the speed of light. So in the non-relativistic limit, it works just fine, but it's wrong in general. Okay, so how do we transform velocities under in Lorentz transformations? That is, in the general transformation that works even for high relativistic speeds, very high uh, relative speeds between two different coordinate systems, two different reference frames. Okay, so we start with just the normal Lorentz transformations that I've shown here, and this is what we wrote down earlier in the lecture, and we basically convert them to the point of view of the of an observer in the unprimed frame. Okay, so again, the primed frame throws a ball and to the right with velocity u. So it's easy for so we know what the velocity is in the primed frame. Okay, and what we want to know is what the velocity is in the unprimed frame. Okay, so first we convert the Lorentz transforms to the point of view of the unprimed frame, and to do that all we have to do is just reverse the sign of beta, because otherwise the Lorentz transforms should be completely symmetric. The only difference is that for frame S the the person is moving to the right with velocity v. To frame S prime, the frame S is moving to the left. So we basically just reverse the sign of beta, so you can see that's what we've done, and then we replace all the t's with t primes and all the x's with x primes, and then you get basically the equation with from the point of view of the unprimed frame. Okay, so remember, the other thing is that we also, in fact, when we derived the Lorentz transform equations, we assumed actually differences in coordinate values. Okay, and so the Lorentz transforms are valid for differences in coordinate values. Okay, and so we basically just rewrite these equations, replacing t with dt and so on, t prime with dt prime and so on, and so then we get these two equations. Okay, now if we divide the second equation by the first equation, 2 divided by 1, we get dx over c dt is equal to this expression. All I've done is inserted what I've put in these two equations. Okay. Now, if we realize that if we multiply both sides by c, because we have this little c hanging out here, and we divide the top and bottom, okay, of our equation of our right-hand side by c dt prime, then we end up with dx dt, which we define to be u of x, is equal to beta times c plus ux prime divided by 1 plus beta ux prime divided by c. Now, ux prime we already know is just u. Okay, so we just replace ux prime by u, and we're left with this. Now, I've used the fact that dt prime over dt prime is equal to 1, that dx prime over dt prime is equal to ux prime is equal to u. So if you make those and obviously beta c is equal to v. So if you make those substitutions and you do this division, you'll find that this is the expression you get. So this is the correct expression now, the correct velocity addition rule that is valid even under the Lorentz transform. So again, for an object moving to the right with velocity u in the primed frame, this is the velocity that an observer in the unprimed frame would measure. So it's just the sum of the velocities divided by this factor. So what we should notice is that when beta is very small, that is when v over c is very, very small, then this term can be neglected with respect to 1. So, and you basically get back out the Galilean velocity addition rule, which is very nice. That's very satisfying, because this should converge to the Galilean rule.